Good day, dear colleagues. My name is Vancho Litovsky. I am a retired professor of the Faculty of Electronic Engineering of the University of Niš, Serbia. My lecture today is entitled SPICE Model of Linear Controlled Capacitance. Here is the overview of the story. It is all about a pressure sensor and simulation of a pressure sensor, which is in fact a microelectromechanical device. There will be several parts of the presentation. The first one will be oriented towards the solutions related to the microelectromechanical system as it is. So it involves partial differential equations, which are usually transformed into a large set or system of ordinary differential equations, and we will discuss the issues related to this solution. Then the complete solution includes mixing domains, which means mechanical and electrical. And we will discuss the issues related to mixed domain simulation. The next topic will be testing and diagnosis, which will be started by describing faults in electronic or microelectromechanical systems. Then a short discussion will be given about testing, functional and structural, and diagnosis, which is most frequently based on fault dictionaries. Having that resolved, we will address the main subject of the lecture, which is black box modeling of the linear controlled capacitance. In fact, the converter of pressure into capacitance in the microelectronical pressure sensor. Then we will see the SPICE simulation results for fault-free and faulty cases, with some advice given related to extraction of features of the responses in order to enable diagnosis in the later phase of the use of the results. Here is the schematic of the pressure sensor we will discuss. This is a silicon microelectromechanical MEM membrane used as a sensing element in a simple system performing conversion of the pressure value into a voltage pulse train whose amplitude is proportional to the pressure. It is an usual switched capacitor structure. An AD converter, not shown in this figure, is following in the next stage of the processing of the obtained pulse train. Let's proceed to the properties and to the way how the membrane is simulated. The membrane is described by the following fourth order partial differential equation, Note that there is no voltage here in this equation. Here W is the displacement of the membrane, the dependent variable. X and Y are spatial coordinates. D is the bending rigidity. P is the pressure, which is independent variable. K is the damping coefficient, rho is the material density, and H is the membrane thickness. In the examples below, we will use L and W 1 millimeter, which means the area of the membrane is 1 square millimeter. The thickness of the membrane is 5 micrometers. The rest are properties of silicon. In the first set of the examples, uniform pressure will be applied of 1 kilopascal. To solve the equations, the following boundary condition is applied to the free edge, y equal w. Two boundary conditions, as you can see. And on the rigid edge, again, two boundary conditions for the equation which is of higher order. To solve a partial differential equation, one has first to discretize the spatial variables. One usually applies the method of finite differences or the method of finite elements. In any case, we end up in a system of n, capital N, equals lowercase n multiplied by m, new ordinary differential equations where the local wij values are now new unknown and time-dependent variables. Here n and m are the numbers of segments to which all L and W are discretized respectively. Capital N may become a very large number. Even in a simple case when lowercase n and m are 100, one gets capital N equal 10,000. That means one has to solve 10,000 coupled ordinary differential equations or system of ordinary differential equations in order to get the displacement of the membrane as a function of the location. If the excitation is variable in time, the problem becomes really time-consuming. Frequently, it may ask for serious amount of computer resources too, since we have to memorize the solutions of all 10,000 equations in time. Here are two examples where the excitation is time independent, 1 kilopascal. The top left figure represents the case where one edge is free, and the bottom right represents the case where two edges are free. In the case of the pressure sensor used, all four edges are rigid. So you can see here how the membrane is deformed and what are the amplitudes, expected amplitudes of the displacement. That would be all about the description of the solution of the partial differential equation describing the membrane. Now we will proceed with the electronic part. Electronics, as it is well known, is ubiquitous. Usually it is coupled with other domains like electrochemical, batteries for example, electrothermal, distribution of heat on a silicon chip for example, bioelectronics, various stimulation systems and processes, etc. The most frequently encountered interaction of electronics is with mechanical systems, microphones, loudspeakers, motors, relays, actuators, etc. Our sensor is typical example of mechatronics. Here the picture is emphasizing the two parts and explains how the new term mechatronic was created. To simulate such a system, we have to formulate equations for both domains, mechanical, as already described, and electronic circuit equations. To come forward, however, with the circuit equation, we need the value of the capacitance, Cs. Assuming the increments delta x and delta y are constant, the capacitance in a given instant may be approximately calculated from this expression, and since there is no feedback to the capacitance for a given time instant, one may solve the mechanical and the electronic part one after the other, with the capacitance recomputed in between. Here you may see results of one simulation. The top line represents the excitation of pressure in Pascal. It is a piecewise linear waveform. The maximum value of pressure is 1 kilopascal. Then the next line is the displacement of the center of the membrane in meters, which means the maximum value here is 0.74 micrometers. Then the third line from above is the capacitance, which, as you can see, reaches 13 picofarads. Finally, at the bottom is the pulse train, and if you look carefully, you will see the time scale is here about 1 millisecond altogether, and within that time the amplitudes of the pulses are following the shape of the excitation of the top line. One can observe the dependence of the amplitudes of the pulses on the pressure, which is almost linear. One should have in mind that despite the fact that the system of differential equations are solved separately, both systems of equations are using the same time agent, t. The time is the same for both mechanical and electronical part, and both simulations are progressing together. For linearly rising signal, the following dependence of the capacitance on the pressure was obtained, as you can see in the picture on the right hand side. Note the variation of the capacitance. For the given pressure interval, one gets more than 100% change of the capacitance in such a small device, which we consider a high sensitivity of the capacitance on the pressure. Note, since the electronic part of the system comprises switches acting in short transient intervals, the time step of the circuit simulation, which is also used to discretize the ordinary differential equation of the membrane, is even shorter, which leads us to a summary that even simulation of a single mechatronic system may be very time consuming and will probably ask for extensive use of computer resources. That will end the story of the classical simulation of microelectromechanical system. Now we will proceed with testing and diagnosis. Testing comprises excitation of the system by a proper set of signals and comparing the responses with the expected ones. If unacceptably large difference is observed, the system is considered faulty and should be discarded. Diagnosis is going further. If faulty response is obtained, one performs search for the location and the type of the fault. Diagnosis helps correction as a feedback. Corrections in all previous phases of production, including the design process, which is the one most responsible for faults. Now, what are faults in an analog microelectromechanical system? First, we will address the switches. As you can see, every switch has at least two faults associated to it. One is stacked open, the other is stacked close. Then you can see this red X, which means open, which means a disconnected line, disconnected connection, broken connection. The number of such possible faults is really very large because every single connection is candidate to be broken. Then look to the green line. We have shorts. The number of shorts is not so large, since in the layout only neighboring connections may be short-circuited. So if they are not neighboring, the probability for short is practically zero. Next, and much more important for analog circuit, is the fact that all values of the parameters such as reference voltages, capacitances, inductances, resistances, all are prone or candidate to become changed or prone of variation, of tolerances, we say. That stays for the parameters of the operational amplifier too. And from that point of view, looking to the electronic part only of the microelectromechanical system, we may have a very, very long list of potential faults. Testing may be performed as functional. That means the system is excited with a set of signals expected to arise during field exploitation. and the obtained responses are compared with the expected ones. Alternatively, test signals are synthesized to target specific faults, usually the ones being most probable to happen. Implementing these signals allows for structural testing. Naturally, for a signal used for testing of a given fault to be synthesized, the very fault should exhibit the following properties: controllability and observability. The first one, controllability, means that there exists a signal which will turn the state related to the fault in an opposite, different value than the fault-free case. The second one, observability, means that the same signal opens a path from the fault location to the output of the system or to the testing point, so that the fault effect becomes observable, not obstructed during propagation towards the output. It is obvious that if no diagnosis is implemented, the functional testing will suffice, it lasts much shorter, and the set of signals is limited. If, however, one wants to perform diagnosis, one needs to follow a different path. Diagnosis is usually based on processing of a fault dictionary. Here we have a table, that is fault dictionary, a table, which contains a list comprising the set of selected faults, signals, and the responses which correspond to each other. For example, fault code 123, which is put in the second column of the table, may mean node 74 stack at 0, meaning short-circuited to ground. Further, test signal code A may mean voltage sinusoidal of amplitude 2.3 volts, frequency of 1 kHz, no phase shift, offset by 0.5 volts, and applied to node 43. Further, fault-free and faulty response may mean time domain waveforms or extracted features including DC, or frequency domain characteristics or extracted features, or both. Reduction of number of test points and measurement type is recommended. That simplifies the measurement and reduces the overall measurement time. The fault dictionary is created by exhaustive, repetitive simulations. The number of rows in it may be really long, as is the list of potential faults. So is the number of simulations. Here is a short table exemplifying the fault dictionary. The test signal was as shown on the right, and the DC component of the output signal is used as the main feature of the transient response. As it can be seen, not always is the difference between the wanted signal and the measured signal conclusive, meaning that in some cases more than one measurement may be performed. I will now visit this table and discuss a little bit of its content. In the first column, we are putting the shorts or shorts used to exemplify, to clarify the type of the fault. Here the first row means fault-free, FF, fault-free, and for that case the DC voltage is 2.829 volts and the deviation is 0, it is the reference. Then we have the fault S1 on, which means the switch in the feedback of the operational amplifier stuck on or closed permanently, which leads to a deviation of 29%, which is fantastic for the cognition. The next fault considered here is the capacitance of the capacitor CR is incremented by 20%, and as you can see the deviation is 5% only, which for some may be insufficient, but for some may be satisfactory. S1 off means that the switch in the feedback of the operational amplifier is permanently open, which means the capacitor CR will be charged permanently. As you can see, a large value of the DC voltage is obtained, which is larger than the power supply of the operational amplifier, meaning that we were not using a real model of operational amplifier, but only a voltage controlled voltage source for amplification. Nevertheless, it is obvious that if a real operational amplifier was used, this value would be the value of the power supply. CR minus means that the capacitance in the feedback is reduced by 20%, and as you can see the deviation is 7.35. And in the last row we have an exception. This is a fault which is related to the membrane. CS flat means that the membrane is for some reason rigid and doesn't change with pressure. And as you can see, even that may be identified. Sorry for this mixture here. There are two types of faults related to the membrane. One is the membrane to be rigid, and the other one to be broken, meaning that the capacitance is reduced to 0. The diagnostic procedure consists of a search through the fault dictionary, last column, fault defect, for the row where, for a given signal, the faulty and the fault-free responses are apparently different. Therefrom is extracted the fault type and the proper location associated to it. Note, this is a simplified description of the process of extracting of the guilty fault. In real life, since the fault dictionary is very long and the responses may be very similar to each other, or the responses of the faulty circuit, a serious problem may arise in distinguishing which fault is related to which response. To summarize the subject of testing and diagnosis, creation of the fault dictionary needs a large number of simulations of the same circuit, while every time a fault is inserted and consequently a new version of the circuit is defined. Note, for every newly created circuit, a search must be performed for a proper signal, which allows for testability of the fault. That further increases the number of simulations. Adding, or better multiplying that, with the time needed for a single simulation of a mechatronic system, we come to an unavoidable conclusion. Something must be done for the testing and diagnosis of mechatronics to become an economically feasible industrial action. We think the solution may be the use of black box modeling of the mechanical part, which may allow for avoiding repetitive solution of partial equations. Namely, the microelectronic membrane, electromechanical part of the capacitor, is not voltage dependent, and if the capacitance is known, it may be substituted in the electronic part, making the sensor all electronic. If so, the remaining problem would be how to model the linear pressure-dependent capacitors and allow SPICE simulation. That will be answered in the next. Black box modeling will be implemented, and here is a short overview of the issue. When no full knowledge of the physics of the device is available, one uses the so-called black box approach for modeling. The behavior is captured by measuring of input, excitation signal, and output response quantities. After that, an approximation procedure is performed over the set of measured data in order to get an analytical expression relating the input and output and being convenient for equation formulation in the circuit simulation process. The choice of adequate approximant is crucial for this type of modeling. In some cases, polynomial interpolation is used in between two measured points, which will be applied below. To our knowledge, there is no general recipe for the choice of an analytical function for this approximation. Main advantage of the black box approach is related to the fact that one doesn't need to have full understanding of the background physics of the device being modeled. Add to that the fact that the model may be developed in no time, enabling the system design based on this component to be implemented immediately and give time to model developers to come forward with a better model based on background physics. Main problem encountered during use of this approach is modeling simultaneously the nonlinear and the dynamic behavior of the device. In such cases, the excitation signal used activates only part of the inner properties of the device, meaning that the model generated based on one measurement may be inadequate for other unforeseen excitations. In addition, the problem of parametrization is present. Namely, the model obtained by the black box approach is useful only for a single device with fixed parameters. If parametrization is preferred, one should use measurements for many components being produced by variation of one or more parameters and include the parameter values into the approximation process as if it is an input signal. Our example is simple. In our example, we will develop a black box model of the capacitance at a fixed room temperature by using a polynomial approximant. Least mean squares approximation was implemented, and this model does not suffer from the above-mentioned disadvantages. Here is the result in red of the first step of modeling of the microelectromechanical capacitance. It was approximated by a sixth-order polynomial, and as you can see, the approximation is quite well and acceptable. Now, having the expression presenting the capacitance as a function of the pressure, we may consider how to insert that dependence into a SPICE-type simulator. The capacitor is introduced into the circuit description by two equations constituting its model, no matter what specific properties it has. It is Q as a function of V and I as a time derivative of Q. Here Q is the charge captured by the capacitor. Vc is the voltage at the terminals of the capacitor. P is a vector of controlling variables. Ic is the capacitor's current and T is the time variable. The parameters P may be time varying, which means that implicitly we presume that the capacitor has a time varying capacitance. For linear capacitor, QC may be represented as follows. QC as a product of the capacitance and the voltage, and here we introduced two quantities, nominal capacitance and the normalized function g of p, which has no dimensions. That is done for convenience. Substituting that in the expression for the current, we are getting an expression which represents the current as a sum of two components. One with time derivative of the voltage and another with time derivative of the pressure. Note the dependence C, function of P or G of P, and its derivative, d derivative C over P, are considered known functions representing the capacitance's properties. In our case, these are represented by a polynomial and its derivative. To get a circuit representation of IC, it will be rearranged in the following way. That may be seen as parallel connection of two current sources. ICV is the first one. It represents a product of a current CO multiplied by dVc over dt, normal current of a capacitance, linear capacitance, and a voltage of a nonlinear controlled source G, product of the current, that is what is in the parenthesis, and G. The second represents a product of three quantities. The quantity C multiplied by dP over dt, the capacitor voltage Vc, and the known derivative represented as a control source. This is known, dG over dP, because this is derivative of the polynomial. it is important to know that P may be a circuit variable defined somehow in the mechanical system, or an independent excitation defined outside of the system. Here it will be considered independent excitation. In this case, two control sources are already available for implementation in SPICE, VI, G of P, and its derivative, dG over dP. The quantity I0, this is a current of a constant capacitor, and the quantity Vk, one should pay attention to this, will be treated, CO multiplied by dP over dt will be treated as a voltage. Now, that means that in this expression, P is considered a current, and we will use an inductance of value CO to get the voltage Vk. So, voltage is equal inductance multiplied by the derivative, time derivative of current. That is, here is the circuit representing the model equations as developed earlier. Note first the top left part of the schematic. Since we have the current of CO, the capacitor CO, we added here two capacitances connected in parallel with positive and negative values, so that looking from the port VCIC, it is as if nothing is connected, but still we have the current as a controlling variable where needed. So practically IC equals to the sum of these two current sources on the right. Now let's go to the bottom. From the left hand side we have an independent source of pressure which creates the voltage V, and that voltage is used as a controlling variable for the voltage controlled current source G of P to produce VI, and it is also used as a control variable for the voltage source dGp over dP, which is the derivative of the polynomial, to produce the voltage Vj. And finally, on the right hand side, we have the current IP, the current P, which is here a controlled source, but it may be the independent too, which is loaded by an inductance of value CO to produce the voltage Vk. So we have all variables to create the two components of the current IC. As you can see, one is IO multiplied by VI, and the other is Vk multiplied by Vc multiplied with Vj. This is the model of a linear capacitor which is controlled by the pressure. Here, the capacitor is embedded into the sensor, and besides the schematic we saw earlier, here we can see the two reference voltages, 3 switches, 1 additional capacitor, CR, and the operational amplifier. the output is at the node 10. Now we may proceed to simulations. Here the red line on this diagram represents the input pressure as a function of time. 1 millisecond is used, as you can see. And two responses of the fault-free circuit are presented. Now this simulation is performed with the model of the capacitor CS. No membrane is simulated now. It is a model which was developed earlier. Nevertheless, as a result of the simulation, the voltage V5 in fact represents the capacitance, and we may see it. This is the polynomial which was created by approximation. On the right hand side we have the pulse train which is produced at the output. As you can see, a small transformation is done for the picture to look nicer, but nevertheless we have a pulse train which is mapping the capacitance very, very nicely. The top edges of the pulses will be flatter if we rise the frequency of the pulses. Now we may play or enjoy by bringing different signals to the fault-free system. For example, in this case, VRF is changed and a triangular pulse is representing the pressure. As you can see, we have a symmetrical response where on both sides of the pulse, both sides of the response pulse train, we have practically the dependence of the capacitance on the pressure. It is practically reproduced. Similarly, we may bring a sinusoidal excitation, and again the dependence of the capacitance on the input pressure is easily recognizable. If we bring a pulse of constant amplitude, we may expect a pulse train with constant amplitudes at the outputs too. Now let's go to faulty circuit. Here a fault is inserted, which is the green line. The switch is stuck at on. On the left hand side is the response to a sinusoidal excitation with VRF 1.5 volts. And on the right hand side is the fault-free case with all the rest of conditions the same, which tell us that there is a strong difference between the faulty and the fault-free response, and that we may choose many of the properties of the signals to emphasize the difference among them. Here the ability of SPICE to change a parameter as a set of values is exploited. So the value of VRF1 was used as a parameter, and 3 simulations were performed. VRF1 1.5 volt, 2 volts and 2.5 volts with Vref1 equals 2 volts is the case of fault-free, while the green and the blue cases are faulty cases. And you can see that not all three are following the shape of the capacitance, but the gain is different. And for that reason, at the bottom, there is enlarged part of the response, and you can see this, the blue one has much larger amplitudes than the others, especially in the region of high pressure. Of course, we may use here the amplitudes, we may use here the DC value as extracted parameters, but we may also use FFT and the spectrum and extracted values from the spectrum to complete a picture about the response and to make easier the differentiation among the responses in the very long fault dictionary which may arise. And that would complete the story I wanted to tell you about this subject. Now let me make some address to all of you. I'm not seeing you while I am preparing this presentation, but still I have a message for you. Yes, electronic is ubiquitous, and it is and will be for a very long time the flying wheel of the human civilization. We as electronic engineers are lucky to be in the mainstream of that. Be aware, however, of the responsibilities which come from that advantage. As you could see from this simple, really very simple presentation, in order to do anything serious in our subject, one needs deep understanding, specialization of his or her subject, but also he or she has to have a broad interdisciplinary knowledge both within electronics and within many other technological subjects to become a member of successful team contributing to the humanity. Thank you very much.